Hey, math class, how's it going? It's Miss Wesley. We are talking standard deviation today as we get into a deeper discussion of measures of variation that tell you about the spread of a data set. And the examples we'll start with are going to be on page 11 of your statistics packet. Your joke today is going to be a drawing. So I'm going to give you this geometric shape, and then I'm going to put that on it. And the joke is, what is that? And get it from geometry, it's a Ray. So Ray Charles, right? There he is. All right, 11.7, standard deviation. Before we get there, we spent a lot of time looking at a type of display that tells you about the spread of a data set. What do you think about this warm-up? Comparing two box plots, the data is 36 best qualifying distances for shot put events for men and women during the same Olympics, and you're going to compare. Well, let's just make a few comparisons. Talk about the spread. That's what today's going to be all about. Which has more spread? I say the women. Women, plural, are going to have a greater range. So women's range is definitely greater. In terms of the entire range from min to max, women are a bunch, right? About 6 in, I guess this is in feet or maybe meters. And while men are sticking around 18 to 21 at the highest, even the IQR, the interquartile range, is more spread out, that middle 50% of women versus middle 50% of men. So you've got more spread. I would say men are, well, what's the word I'm fishing for? What's the adjective that means they are all bunched around one area? We'll say that they're more consistent. More consistent, meaning a lot of the distances are going to be around the same value. And we'll say unfortunately, we have to admit that they throw farther overall. So with apologies for my sloppy handwriting there, you see that overall men's numbers are bunched up around really just, this is the top 25% of women that are getting close to those male numbers. Okay, now let the fun begin. To find the mean of a data set, you sum the data values and you divide by the number of values. We've talked about that. You can use summation. I'm going to teach you a little bit of new notation today and possibly a new Greek letter. Not sure if you've heard of it. To measure how data deviates or varies from the mean. So the mean is nice to know about. If I gave you guys a test, I'd like to know the average score. But it would be cool to have some other statistics that would tell me how spread out the values are on average from the mean. Is everybody doing consistently, like these men's shot puts around the same distances? Or is there a wide variety of data within the set? In order to talk about sums, let's get some terminology here. Some Greek letter summation notation. The capital letter sigma, capital, very important, versus lowercase, because we're actually going to come back to lowercase sigma. But this is capital sigma, like that E looking kind of thing to indicate a sum. Side note, if you don't know your Greek alphabet, you should learn the Greek alphabet for fun, and it helps you on crossword puzzles. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta. Okay, I'll stop there. With sigma, you're going to write limits below and above the Greek letter to indicate the first and the last terms that you're adding. So for example, here's one that I'm not going to expand out by hand, but this is a lot of terms that you want to sum. So sigma means you're going to sum a bunch of terms. What term do you start with? Well, this is going to be the number that's below. The sigma is going to be your lower limit. So that's a 3 here. Lower limit of summation. And then the one that's sitting up top, the 108, is the upper limit. So it basically gives you boundaries, a starting point, and a solid ending point for the values that you're going to add together. Start with 3. What are you going to do? Plug in 3 for n. So 3 squared is the first term, and they call this a series that you're going to add together. You continue counting up the integers until you get to 108. Now, I will not write all of these, but 4 squared would go next. 5 squared, we'll say plus dot, 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 until you get to 108 squared. So there's a way to do this that's a bit quicker using computers or calculators. For now, I just wanted to write it out expanded so you get the idea. Here are some that are a little bit tamer. You see these examples 1 and 2. We're not adding together too many terms. This is great for practice. Try number 1. It says find the sum. We're going to try this by hand. Where do I start? Look at the bottom. Start with a 1. The first term is going to be 2, and I'm going to even show the plug in here, which is not completely necessary, but it's 2 times 1 minus 1. Next term, you're counting up the integers, so 2 times 2 minus 1, plus, because this is a summation, 2 times 3 minus 1, plus 2 times 4 minus 1. How do I know when to stop? I got to look at that top number. Last one, 2 times 5 minus 1. So that's the entire thing expanded out. I've taken up most of the space for the problem. Really, it's as simple as adding 2 minus 1, so 1, 4 minus 1 plus 3, right? 6 minus 1 plus 5. Looks like I'm adding successive odd numbers, 1, 3, 5, 7, and 9, and you end up getting this expression equal to 25. Not so bad when you only have to add 5 terms. Let's try one more for the fun of it. Start at 1, plug it in for n, so 2 to the 1 plus 2 to the 2 plus 2 to the 3, whoops, plus 2 to the 4th. And I'll stop at 4 because I see that sitting right on top of the sigma. And you're adding 2 plus 4 plus 8 plus 16. So add those together, and you get that this summation comes out to be 30. Okay, so just a little aside, you're going to see this notation maybe once or twice more this year and a little bit next year in pre-calculus. Measure of variation. All right, so now we've spoken a little bit about a few measures of variation like range and IQR. Tells us about the spread of the data. Now I want to add to it some really important ones, variance and standard deviation. These measures describe how the data in a set are, we're going to say, spread out, which is valuable info when you're talking about data. Notice these little symbols after variance and standard deviation, and I don't want to confuse you by writing this differently, but I write my lowercase sigma a little bit differently than this particular font does. So it's something like this for standard deviation, or you can draw it like that. That's usually what I'm going to draw. Both of these are a lowercase sigma, which stands for standard deviation, and we'll define it as, it's called population standard deviation, but I'll get to that in a second. If you square it, you get variance. Both of these statistics show how much data values deviate from the mean, how far they are spread away from the average or the center of the data. It's kind of funny that one of them is sigma and the other one is lowercase sigma squared. It's like, what does this one tell you that that one doesn't? Why do we need both of them? Well, when you'll see in a second, we're going to calculate standard deviation, and you'll see that you actually get to variance sigma squared before you get to standard deviation, just plain sigma. So it's kind of a necessary step on the way to getting standard deviation, but these go hand in hand. Anything this tells you, that will tell you as well. In a way, variance is kind of silly. If you know standard deviation is high, you know you have a large spread in your data, and variance will follow suit, right? If sigma is high, sigma squared is also going to be high. So variance, not as important. Standard deviation is the huge, really, really popular measure of spread. We're going to go through these steps, but I think it would make more sense to try to explain these steps as we're going through an actual problem. So give me 1 second here. I want to put one other thing in this space so you have it right on this page. Lowercase sigma, or sigma sometimes with like an X subscript. Can you write population, put the word population there? Because you'll see sometimes there are 2 types of standard deviation, so I'll put that afterwards, standard deviation. It is what it sounds like. It's how far, on average, the data values vary from the mean or deviate from the mean for the entire population, every piece of data in the set. Versus this other one, I'm going to put this in parentheses because our textbook just doesn't happen to use this statistic as much. It's capital S of X. And that S does stand for standard deviation, and this funny sigma looking thing kind of looks like an S. But if it's just an S of X, it's going to be the sample. S is for sample. Standard deviation. You may ask, what's the difference? There is not much difference. I'll explain how you get sample standard deviation once we talk about sigma, the population one. Just know that sigma is the one that's used more often for us in our studies, and it's about an entire population, versus S of X, which is just supposed to be the standard deviation of a sample, a subset of the population. Okay, now I want to get to some actual numbers so we can start seeing if this is going to make sense. Step 1, take the numbers, you're going to find the mean, find the average. Okay, go ahead, feel free to pause the video, add up these numbers, and divide by 5. See what you get. Okay, then unpause. You get the mean, and this is all these data values are going to be rounded. It's going to be about 7.4. Okay, so that's the mean of the data set. That's step 1. I'll check it off. Step 2 says we're talking about variance or deviation from the mean, so you're going to find the difference of each data value from the mean. What would be good in number 3 is if we can organize this into a table. So we're going to call the data, the points of data, just the x's. And I'm going to list them vertically, 6.9, 8.7, and so on. So give yourself some room because we'll have a couple columns here, 4.8 and 9.0. We're trying, have a calculator handy. I should actually do that too. Trusty calculator, but we'll try to do as much as we can just looking at this data. Okay, so now step 2 was the next column heading is going to be the difference of each of these values from the mean. So the data value minus 7.4. Some of these are going to come out negative. Feel free to pause the video and do the subtraction. If you do 6.9 minus 7.4, you get negative 0.5. 8.7 minus 7.4, 1.3 away from the mean. 7.6 is only 0.2 away from the mean. 4.8 is negative 2.6, it's 2.6 below the mean. And 9 minus 7.4 is a 1.6. I want to pause here. If I added these red numbers, can you guess what I would get? I'm going to write this in fancy notation. If I summed, capital sigma, summation, all the deviations, I'm going to add these all up, crunch the numbers, and I get a 0. It tells me nothing. So my question is why? Should I have seen that coming? Well, yeah, each of these, if you add them up, you're going to be just as negative below the average as you're going to be positive above the average. By nature of how you calculate an average, the sum of this column 0. So that's why we can't just use the deviations. What we're going to do in the next step, we found the difference. Now we're going to square each difference for 2 reasons. We're going to square each difference. Reason 1 is it'll take away the problem of us having negatives and positives just canceling each other out. So that's good. It'll make all these values positive. Reason number 2 is it's going to give more weight to far off values because when you square bigger numbers further away from 0, you get, some exaggeration in the value. So it really is going to emphasize the differences. I'm just going to take these red numbers and square them. I'll write them here. 0.25, it's this number squared. 1.3 squared is 1.69. Next one squared is 0.04. Next one is 6.76. Notice we're getting all positives, 2.56. This is the column that I want to add up. I think it says that next. After we square each difference, we're going to find the mean of these squares, the average. So let's sum this column, fancy notation sigma, x minus x bar squared. And I'm adding up all these black numbers to get a total squared deviation of 11.3 units, 11.30 when rounded. Now I want to average. I want to follow these directions. So that is, we'll say that sigma is going to be that sum, 11.30, divided by how many values we had originally. So divided by 5. And this is your, actually I said sigma, I meant sigma squared, sorry, because it's the squared variation. And that's going to be roughly 2.26. This is your variance. You'll see that in the steps above, that sigma squared, we got these two, equals the sum of the squared deviations over n, the number of values. Last but not least, let's get standard deviation. If you have sigma squared, you have variance, you can square root that to get standard deviation. So square root of 2.26 is roughly, what, 1.5. This is the big statistic that we're going to use a lot. This is population standard deviation. And that's the one that we'll use. I mentioned how sample standard deviation is pretty similar to that, so why have something different? I'll tell you, in the calculation, the only difference is that n becomes an n minus 1 when you're trying to calculate this. But for now, focus on sigma, focus on population, and I'd like to write a sentence that summarizes what we just figured out. This is really important. I would copy this down. So I know I can interpret an average. I know I can interpret a range, an IQR. How about if you're asked to interpret a standard deviation? So write this sentence down. On average, I'll put AVG for average. The data values are going to vary. So vary 1.5 units from the mean of, what was the mean? 7.4. So for whatever, I was never told what these numbers represented, but on average, all the data values are going to be about this many units above and below the mean, which is a nice statistic to know about the data. Stay tuned for the next segment where calculator shortcuts are going to come into play. All right, talk to you soon.